Hello and welcome to another episode of the OPELX podcast. This is a part of the Open Power Electronics project, or OPELX for short. Visit us online at opelex.net. That's opelex.net for past episodes, show notes, and more. This podcast is hosted by me, Lalit Patnaik. Currently, I am a power electronics engineer at AVL in Graz, Austria.
And I am Abhijit Kshirsagar, currently a faculty member at IIT Dharwad in northern Karnataka. Critical support behind the scenes comes from Sudarshan Karthik and Najat Abdul Aziz. In this podcast, we talk to leading experts in academia and industry in power electronics and allied fields. We hope you find this useful and entertaining. Today we have another guest from the industrial side of things, Dr. Girish Kamath, who is joining us from North America. Dr. Kamath, you've been a practicing engineer in industry for many years now. You have a lot of rich experience in multidisciplinary engineering projects, and we are happy to have you on board. Could you give us a brief introduction about yourself and where you're located and what you do?
Oh, thank you, Abhijit, Lalit, and Sudarshan for inviting me to this podcast. I really appreciate chatting with you. Now, with regards to where I am right now I'm located in Hanover, New Hampshire. I work for a plasma cutting company, which is essentially a mechanical engineering company. Mm-hmm. And for the past 20 years, I've been with this company, and I have been designing power supplies for plasma cutting applications, which involves, in particular, designing the key components that goes into the power supply. That's the magnetics, which is the transformer, the components that go into the converter. So we have a power converter, which is used for maintaining the gas in the plasma mode. And so the components that go into the power converter, basically the powertrain, the semiconductors that constitute the powertrain, as well as the cooling system for the power electronics. So that is as far as the power electronics is concerned. The other thing that's unique about plasma cutting, which is not seen in standard power electronic applications like motor drives, for instance, or UPS systems, which is where I had worked prior to moving to this company. And the uniqueness is that because it is predominantly a mechanical engineering application, which involves controls of gases, because remember, the basic core principle of a plasma cutting application is to use gas, which is air, it could be oxygen or nitrogen, to convert it into plasma, which is the fourth state of matter. And the reason for doing that is that we then use the very high temperature of plasma, which is of the order of tens of thousands of degrees of Kelvin, to melt and cut metal. That is what the device is for. And to do that, we use a high voltage, high frequency circuit, which then triggers the initiation of the gas into plasma mode. And so that is based on the Tesla coil resonating frequency principle. And I'm involved with the design of that as well. So in that sense, this particular nugget is something that's unique to plasma cutting, which is not normally seen in other applications. Before Hypertherm, I was working in a motor drives company, where again I was involved with designing the powertrain for standard induction motor drives. In the course of that, I got involved with power factor improvement, power factor input line current power factor improvement, in which I then designed a multipulse transformer, which is a standard technique for improving line current power factor. And then going further back, I was a graduate student at University of Minnesota, where I completed my graduation there, master's and a PhD.
Right.
And so that in a nutshell is my career here, or in the United States, going back all the way to 1994. So this in a nutshell is what I have been doing over the past 27 years here in the US.
Yeah, that's really interesting. I mean, covering such a interdisciplinary kind of range of applications in the sense, I think you mentioned this earlier in a conversation about the perspective of an electrical engineer working in a non-electrical context. That's a completely different kind of way of looking at how you apply, let's say in this case, power electronics to cutting applications and
yes.
the perspective.
Yeah, I'm glad that you brought that up, because that is what I think has made me continue my stay here, is this unique perspective which I never had working in a non-electrical environment, is the ability to imbibe ideas not related with your field and apply it, actively apply it to your work. And that was something that was that I had never experienced before, because till that point, and actually I have had very good experience in India as well, because I had worked for 6 years after my graduation from my BTech graduation. So I worked in India predominantly in the power electronics industry. I had a very good experience there. But it was purely power electronics. And that was it worked very well from a career perspective, because it helped me to discover myself, so to speak, and kind of gave me the confirmation that yes, this is the career path that I would like to pursue. And so it was very useful in that sense. And it gave me the maturity to then explore other areas, which is not related with electrical, and which is what happened here in Hypertherm. The perspective that you get is really something that is not just enriching from a personal perspective, but it is also from a professional perspective as well. It is highly beneficial. You automatically gravitate towards developing practices that yield top-notch results. And it's good to be in a place where you do not have to make a case, a case meaning in the sense that even let's say, imagine you were in a purely electrical company, and you somehow come to the conclusion, maybe you attended a conference or something like that, where you come across this paper which gives you this perspective from a non-electrical side, some mechanical engineering practice, which you are convinced at an individual level that if you apply it to the design of a particular component, would really yield benefits. But to make that case in a purely electrical company is very difficult, to get those resources, the tools that you need. It's very difficult. But that for me was already done, taken care of, because the mechanical engineering, from a mechanical engineering perspective, those tools were already available. And so I had to just piggyback on the existing infrastructure and then, do my job.
Can you give us maybe one or two examples where, let's say, as an engineer or as a person who's still on the learning curve, how would you say that being in a mechanical engineering company, you solved a problem differently, or you had a perspective that was different?
Yes.
Compared to, let's say, being one electrical engineer out of maybe hundreds of electrical engineers in a core electrical
company?
Great
question. So let me take, as I mentioned at the beginning of our conversation, that my job here involves designing magnetic components, which is part of our the power converter that feeds the plasma arc. Now, one of the main components in magnetics is the line frequency transformer, which acts as an isolation device from the incoming three-phase input. It serves two purposes. One is isolation, and the second thing is it is part of the multi-pulse line current power factor correction circuit. There are diode bridges connected on the secondary side of the transformer, which help to improve the power factor. So it does these two things: power factor improvement and isolation. Now, so I joined this company in 2001. Prior to 2006, 2007, the methodology of designing this component for our power supply was we would send a terminal specification to the transformer manufacturer saying that I want this transformer, and just to keep this perspective, the transformer has to be rated for the power rating of the converter. So if I am designing a 20 kilowatt converter, then I have to design a 20 kilowatt transformer. So it has to handle the power rating.
Right, obviously.
So, and for the systems that I'm involved with, it's we have to design power converters from 20 kilowatts all the way up to 100 kilowatts. So imagine this is the range that we are talking about. So the methodology was...
So just quick question, is that 20 kilowatts average, or is that peak, or is that, pulsed?
No, this is continuous power rating, three-phase power.
I see, but the converter also has like a continuous
just to go a little bit more, I'm glad you asked that question. Plasma cutting loads, imagine you're cutting metal. So there's a big sheet of metal and you're cutting metal. The duration of the cuts can be as long as a minute. So you are cutting the thing for a minute, and then you stop, and then you choose a new position, and then you start cutting again. Cut durations can be from 2 seconds all the way up to a minute or even an hour. 1 hour you could be cutting continuously.
Oh, wow.
So in that situation, the duty cycle, which if you want to take advantage of it, which would be a function of the thermal time constants of the power supply, at 1 hour, you can safely say that all the components would have reached their steady state from a thermal time constant perspective.
Yes. So basically you have to rate the whole thing for continuous operation at the peak
Exactly.
Power.
The way we went about doing it was we would write the terminal specification, design this transformer, 20 kilowatt power rating, input 3-phase 480 volts, 60 hertz, output 200 volts. We have two Y delta windings on the secondary side for 12 pulse rectification, and design one and give it to us. And so the transformer manufacturer, in his infinite wisdom, would, and based on his previous experience, because he has been supplying transformers to us, and so he would send us a prototype with thermocouples for temperature measurement. We would get the unit, put it inside the power supply box, and then we would run it. We would do a heat rise test. And if the temperature is less than X, let's say 150 degrees, say pass, that's it. Now, it's perfectly, this is a functioning methodology. We have been using it, and that's how we qualify transformers. But as you can imagine, because it is highly empirical, the incentive for optimization is limited, because each iteration takes about 6 to 8 weeks, which would then impact the deadline of your project. And so once we have a unit which is giving us which meets our spec, which is a temperature rate value less than 150 degrees, we freeze the design at that point. That in itself, we noticed that, of course, it worked we managed with this methodology for the lower power units, the 20 kilowatt and even at the 45 kilowatt level. But we hit a roadblock at the 80 kilowatt, because what we found was that there was now a pressing need to actually do that optimization, because it was really hurting our profit margins. And so there was a tension. And so when that happened, there grew a need for an alternative method. And how did that happen was, now there's a little bit of a chronology involved, was that just 1 or 2 years prior to this occurrence, during one of our other project briefings, one of my mechanical engineers, that's where the mechanical engineering influence comes in, he presented the results of a project that he was working on, where he was involved with optimizing some mechanical engineering related stuff. And in that, he demonstrated the use of a flow thermal tool that he used to do that particular optimization. When I saw that, it immediately struck me that, well, if in the end of our magnetic component qualification, we look at thermal temperature ratings to confirm its qualification, it makes obvious sense to take that tool and apply it for magnetic component design, right? So since that tool was already available, that's a given. The missing piece was an electromagnetic tool. We did not have an electromagnetic tool to fill the gap. And so I had to do the job of convincing my team and the group, and they readily agreed. And so that is how we changed the methodology, whereby essentially what we did was we do the design, the analysis upfront, the analysis of all the key factors that influence the performance of the transformer upfront. In the sense that we recognize the fact that the transformer is not just an electromagnetic device, but it is also impacted by flow and thermal effects. Because in the end, it's the temperature rating of the transformer that determines whether it meets our specification or not. Imagine if you were to incorporate all these effects into the design itself. Then naturally, by nature, in a perfect world, of course, if you are able to represent those effects accurately, then naturally you will produce a design which is customized to fit in that environment, because it has by definition incorporated all those effects at the outset. The effect of the fan, the effect of the grill, the effect of the neighboring components, how they influence the airflow. And then from an electromagnetic perspective, of course, we are trained as electrical engineers to handle that. But overlay these key physics, the physics that represent these effects, into the design stage. You will automatically, because in the end you are emulating how the device works in reality. And the way the device works in reality, like Mother Nature, it works in an interactive and non-linear fashion. So that is how this idea emerged. At least, it is known in industry in other situations. It is not new from a practice perspective, because there are tools that already are in the market. They were there in the market. They have been there in the market for at least 20 years or more. It is just a question of recognizing that. You are in a situation where you recognize that, this is a way to address the problem, and then being able to apply it. And so you need all these things to converge to actually realize and experience that.
So basically, I think your statement is sort of a justification or a plug for multiphysics analysis or simulation.
I'm glad you brought that terminology up, and that is what it is. So multiphysics, it's good that you brought that terminology up. I was trying to refrain myself from using that. These effects, when I said flow, thermal, and electromagnetics, you could argue that there are different ways of representing these effects or modeling these effects, and that's perfectly fine. We need to give space for that. the multi-physics way of doing this is actually to apply the fundamental equations that represent these effects. So that is one way of doing it, and that's the way that I am using here. So I have an electromagnetics tool that actually uses the fundamental equations of electromagnetics. That's our Maxwell's equations. And similarly for the flow, there is Navier-Stokes equation, which is actually nothing but Newton's second law, if you want to. I'm just saying that from a very, very layman perspective. And the third is thermal effects, which is coupled with flow effects, because they are much more.
So I suppose in some sense, being a double E person in such an interdisciplinary team, I think you have the expertise of mechanical engineers, let's say with thermal expertise, with CFD expertise, so that you basically bring to the table your experience with electromagnetics. And then, you can rely on those experts and, come up with a good model or a good simulation where you can actually validate
You're
that.
right. So I can speak their language. Let me put it that it's like speaking. I can speak to you in Marathi and, like that. Being able to
True.
communicate. See, the key thing is you have to be able to communicate in a language which the other person understands.
So let me ask you, is that something that you learned or, picked up being in a company like that? Or do you think you would have done that if you had been, let's say, in your previous drives expertise or in a drives-based company as well?
That's a good question, and it's a hypothetical.
Of course. But what's your best guess, would you say?
Be able to. But here's the thing. What happens in a purely electrical company, and especially I worked in a large electrical company prior to that, and typically what happens in such situations is it is not that these effects are not recognized. Everybody knows that transformer, it is impacted, or magnetic or motor. You have to incorporate these flow and thermal effects. Non-electrical effects have to be incorporated in the design, and at a global level it is done. The point here is that I would not have had that exposure at an individual level to interact or even to be able to use those tools myself. That's the difference. You would have had a department of thermal engineers in a big company of mechanic. Okay, so you just do your electrical calculations. So the copper loss is so much, core loss is so much. Okay, I hand it over to my
so is that so do you think that that is somewhat related to being in a startup type? I hesitate to use the word startup, but do you think that experience is richer in a startup quote unquote environment where sometimes you have to think of a lot of these things yourself and not have, as you said, a team of mechanical engineers
100%
sitting
absolutely
to do that.
I think you hit the right nail on the head. So the key thing with startups is that there are not many people around, so you have to use the resource that you have to its maximum. And so problems, by definition, because they are multifaceted, give opportunity to each of these individuals to address them more often than not in fields that are outside their areas of expertise. So yes, absolutely right. A startup situation would have provided a similar such opportunity. Normally have this situation in companies where there are not many people, say 15 to 20 people of that order. That's where you have exposure to all these opportunities, and that's what I had during my which is where I actually learned the tips and tricks of power electronics, working for this small company in Mumbai.
Yeah, Dr. Kamath, one thing that I really like about what you said right now is the fact that real world problems are so much more multidisciplinary than the way we learn things in the academic side of things. So I think just based on this fact of how, let's say, engineering in the real world is more like multiphysics, multiple phenomena, multiple domains coming together. And also the fact that the design process then becomes quite non-linear and iterative. And I think you have some interesting ideas on how we can take these lessons to maybe change the way we teach certain things in academia, or maybe restructure the curriculum in a certain ways.
Sure,
Could you
sure.
share your thoughts on
I
that?
I think so. Let us actually step back a little bit and look at the way our thinking is structured, and start from there. You will notice that we think in a linear fashion, right? So, for instance, let's take the transformer as an example. We know that the transformer is an electromagnetic device, and it is also impacted by flow and thermal effects. Now, look at the typical design flow of the way the transformer is designed. So, you have an electrical engineer, he does the electromagnetic part, then he hands that stuff to the flow engineer, or the flow/thermal engineer, who does his part, and maybe there is some iteration there at the global level, maybe, I think naturally, but the point is that each individual is thinking in a linear way, right? Now, go back a little step further. You know, when I underwent the electrical engineering program, I was just focused on electrical engineering. I had no exposure to non-electrical engineering material, minimal at best, maybe a fluid mechanics here, there, very perfunctory. And even go down a little bit further, you will notice that the emphasis in our curriculum is mainly on linearization. At each point, you know, even going down to calculus, you will see that we tend to linearize and then use Taylor series or whatever, you know, because it helps to analyze. There's no question that linearization is a powerful tool and it should be used. I'm not saying it's an either or situation. But the tendency to use linearization across the board in each and everything, it's natural and I am part of it. But it has its limitations. And now you hark back to the real world. So I'm really whipsawing here. You go to the real world doesn't work like that. Mother Nature doesn't work like that. It's highly non-linear, it's highly coupled and complex. Linearization makes things simple, but it can be reductionist, make things too simple. So, because we have this very narrow view, that is actually, we are bringing that from the way we have been trained. And we take this training all through our career.
Yeah, we get tied to it, I think. We've always used those tools and then we sort of rely on them almost as a crutch and have difficulty thinking outside those lines.
True.
Yeah.
So here's the situation. Your practice is now the way, now that I have this exposure to multiphysics, it is now, I'm now reflecting back. I'm now going back in time and trying to think that obviously there's a big difference, right, between the way you're practicing and the legacy of your training and all that. There's a tension going on there. So that is where the historical, it's good to have a historical perspective. And I've not done a deep study of pedagogy and stuff like that. I think that is where I think because you're deep in it. It would help you to learn a little bit about how concepts were taught, you know, electrical engineering or anything, how they have evolved over the years, you know, say going back 100 years. And I have not done that study yet, but it would be very useful. But my guess is, and this is just my guess, and I'm saying that from my own personal experience, one, of course, in India, when I was undergoing, going through the program, and then second in Minnesota, where I joined the program in 1994. And it gives me 2 data points over a period of 8 years, because I graduated in 86 from with my BTech, and then I joined the graduate program in Minnesota in 94. Undergrad program in India, and then an undergrad program in the US 8 years later. There are some key differences, but but there were some similarities as well, some very eerie similarities as well. And ironically, the similarity was in the teaching of the most fundamental topic, which is electromagnetics. I mean, we all know that electromagnetics is the fundamental, is the building block, is the platform on which everything electrical stands. The material was almost the same as what I recall learning more than 8 years before that. So at that level, at the fundamental level, the pedagogy was the same. We would learn about parallel plate capacitors, and also learn about uniform fields of plates, infinite planes, and so on and so forth. Almost the same. And then another similarity was the disconnect between this fundamental course of electromagnetics and the rest of the coursework. Right? I'm making this statement, and correct me here. I'm making the statement there is a disconnect between the fundamental course of electromagnetics and the rest of the coursework that is taught. My point here is, can you connect those fundamental equations, Maxwell's equations, those constitutive relationships, all those things? For example, J equals sigma. I don't want to write. But the point is, if you can make that connection with the design of the components that you are involved in. For instance, we use the Kirchhoff's laws. For at least at that point, if you know how Kirchhoff's laws are connected with the fundamentals of electromagnetics, maybe that has been taught. And then further up, how do you apply these equations to the design of the components that you are practically involved in? That disconnect is there.
Yeah, you are essentially talking about this kind of a strict divide between the analysis of systems and the design or synthesis of systems, where the way of thinking is actually quite different for both of these. And to combine both of these ways of looking at engineering systems to get a common understanding of this whole thing, that is where I would say you are heading to, in terms of what happens when you teach things or study things, and what happens when you build things.
I think that is one
very
nicely summarized, Lalit. That is definitely one problem. But the other problem I'm trying to articulate is at the curriculum level, at the pedagogy level, the inability to present a compelling case for connecting the fundamentals of electrical engineering instead of talking about abstraction. Intimately making that connection with the rest of the coursework. I feel that it is still there. At least it was there. I mean, I had that question for 25 years after I graduated, till I started using this. Then it started falling into place. And even now, I'm not claiming. So the point here I would like to emphasize is that I don't have a full understanding of how, from a cognitive perspective, that I understood this completely. No. But the fact that I'm using it, I'm applying it, is the first step to kindle the curiosity of now addressing the how and so I understand the how part of it, but now the why part of it, how to make that connection, which is where the curriculum people on yours, you step in and then establish that why part of it. The practice basically is making the assumption that the why is figured out, but applying it, the how part of it, into actually creating this stuff that we are designing, the stuff that we are supposed to.
Yeah, I think you made a very good point there, and me being the only academic on this call, I think a bit of an unfair burden on me, I would say. But I agree with your point, and I think it's given me some food for thought about how I teach basic courses myself. So I have just one comment to make here. So one of the things that when we talk about these physics-based quote unquote the fundamentals, right? And historically, the lack of computing power has made it necessary to use thumb rules, engineering insights, and basically if it works and So how much do you think a reliance on, let's say, FEA or, brute force computing, being able to simulate this, how much do you think that makes a difference in engineering judgment practice versus being able to synthesize design and so on?
I think I'm glad you used that term, because computing, that is where the historical perspective came in, and I'm glad that you mentioned it, because it saves that much time for me to actually make that case there. That is what the pedagogy, if you see, the pedagogy, I think, had a genuine excuse. That even if they were to really formulate a material of the kind that I was imagining, there was no way you could implement that, because the computing power was not there. It was too expensive, and we just did not have the ability to realize it. But that excuse is no longer there. And here's the other thing that I have observed from my practitioner's perspective. Remember, and we have mentioned this in my previous conversation, that when I joined this company in Siege, in Devdar Electro Design, they were my mentor there. He was Surya Narayana. He had already designed a switch mode power supply using MOSFETs, which was the first time it came to my knowledge that there is something called a power MOSFET. This is 1987-88. Okay, number one. Number two, so why am I bringing that topic up is just to give you an example of the fact that here is where practice was actually leading pedagogy.
Well, I'm sure that in industry, of course, has been leading sort of academics in that sense that, obviously industry wants to do the latest and greatest.
Exactly. And then multiphysics is another case. Multiphysics is another example.
True. How do you balance, let's say, the reliance on simulation or reliance on tools? Because a lot of times what happens is, the students sometimes become too reliant on, just put it in the computer, see what comes out, versus knowing those rules of thumb. How would you say a balance between those can be reached?
Very good point. And this is where you have to rely on scientific methodology. When you know your limitations, then what you do is you apply the basic scientific principles. And what is that? Basically trust but verify. You put in place verification methods. So my point is, there is no excuse for an empirical verification. Multiphysics or any fancy method, at least to my knowledge, does not eliminate the need for empirical verification. In the end, that's the gold standard.
So Dr. Kamath, I was just thinking that it's probably something that had to be brought up because you are also a big fan of this, and that is the role of mentorship for engineers.
Sure.
And I just thought maybe you want to mention a bit about the mentors who played a big role in your life or your career as an engineer, and also your philosophy of how, let's say, as we grow with experience, how we could be good mentors for younger engineers. So two things: your own mentors and the way to mentor younger engineers. I
appreciate that question. So there is no doubt in my mind that I'm here because of so many people who went out of their way to help me. Both teachers, both from the academic area as well as from industry. I should start with my BTech advisor, actually, Professor V.V. Shastri, with whom I have been in touch, but of late and I think it is my fault, he was very instrumental in helping me at a critical juncture in my life when I was actually trying to make the transition from industry back into academia while applying for graduate school here in Minnesota, especially then. And I always I met him on a couple of occasions after my graduation. So we were in touch. I actually met him in IIT Madras and for advice and so on and so forth. So he has been very instrumental in helping me out. Then from the industry side, and I mentioned this before, Mr. Surya Narayana, who actually gave me the opportunity to work with him. and which is what helped me to really discover myself. Worked for this company called Devadhar Electro Design, and then Mr. Sanabatti, with whom I have been in touch, who also I would consider him as one of my mentors. I had the shall we say the privilege of working with him in Devadhar Electro Design, and this is where I learned all the tips and tricks of which I use even now in my. This was all
this
in
is
the
all
late
in the
80s
90s,
and early
right?
90s. Correct. This is before I moved to I joined the graduate school here in University of Minnesota. So the point here is from a practical perspective, especially I think So I was basically an apprentice to both Mr. Suryanarayana and Mr. Sanabatti, and I feel that was a big, huge. It really helped me since then, and I can never forget that. And then, of course, I owe my gratitude to Professor Mohan for giving me the opportunity to join his group. And so, what it helped me was to fill a critical gap in my skill set. So, with Mr. Sanabatti and Mr. Suryanarayana, I learned the practical aspects of power electronics, actually soldering and stuff, and blowing things up and so on and so forth, troubleshooting, all those things, how to apply theoretical concepts. That is where actually one of the other things that I had a question in mind was, why do we learn control systems? And so that question got answered then.
Would you like to give one or two examples? Let's say some specific examples of how they guided your either career development or your skill development, or where they took an initiative or did something that was not ordinary.
But essentially, if you are working in a small company of less than 20 people, where the business model was to turn out products customized to the needs of that particular customer, the environment was probably not very different from a startup, where you basically have to fill in to satisfy needs which are outside the area of your expertise. And so it naturally you had to learn about transformer design, even though they didn't teach you that in well, if they did, well, whatever. I mean, or learn how to make printed circuit boards, how to troubleshoot stuff, how to assemble mechanical, look at from a mechanical perspective, learn to diagnose failures, which they don't teach you all that. I mean, so the environment was naturally conducive for you to learn all these things. And so, given the limited resources that we had, we all had to put our heads together, no matter who you were. So our organization was so flat that it was me and Mr. Sanabatti. We used to sit together on the bench and try to figure out what's going on. Or me and Mr. Suryanarayan. I mean, those days are still fresh in my mind.
Basically, you had to done whatever needed to get it done. Would you give any specific advice to young people to be good mentors? Or, when I say young, meaning people like us who are young engineers, how can they be good mentors to their employees or their teams? Could you give some specific pointers?
So the first point that you need to figure out is what are his likes and dislikes, and then encourage him in that along those lines.
What you're saying is, find out their, innate skills and their desire to be where they want to be. And then you're saying, if you're not the best person to guide them, then step out of the way. So one thing that, comes to mind, we of course know your career trajectory, but, unlike, let's say, a lot of other people who have a bachelor's, then they go immediately into a master's and then go immediately into a PhD and then get into, let's say, an R&D career. You have a somewhat, let's say, not a very straight line path.
Non-linear.
Could you talk a little bit about that?
The transition from my bachelor's to industry was very natural because I was burnt out by that time. I really didn't want to study anymore. And neither did I follow the traditional path of my colleagues who were with me during my bachelor's. They were charting their course to the United States and stuff like that. I didn't even bother, which was, people were shocked when they when they learned about it. But yeah, I just didn't want to do any of that because I was burnt out by then. And so I worked in industry for 3 years, and which is where as I said, I discovered myself. I had the first inkling that I wanted to work in power electronics was during my final year project. That was a good thing, even though the project didn't work out well. But I got to know Professor Shastri very well, and we were in touch. We've been in touch. We were in touch for at least 25, 30 years.
So I have to interrupt you and ask. We know that you went to IIT Madras for your bachelor's, and you were not in the the electrical engineering branch. You were in the electrical power, I believe it was called.
Electrical power. Yeah, so they had two. I'm glad you brought that up. So they had two sub branches: electrical and electronics, and electrical power. So I was in the electrical power branch. Correct. So I did my final year project under Professor Shastri in power electronics, and that is where I kind of felt that yes, I think because it had the right mixture of analog and power and stuff like that, and so it's a good place to be, at least intuitively. And then of course I went into industry, and after a change of jobs, which is then I started working at Devdhar Electro Design, which is where I really learned the ropes, so to speak, by becoming an apprentice. That was where I really felt good about being in this field. And then, but what it did was two things. One is it helped me to mature on the job, learn by doing, as they say, and also helped me to reflect on what do I need to do to be a better power electronic engineer. And that is what motivated me to do a master's. So I wrote the GATE exam and then joined the master's MTech program in IIT Bombay. This was in '89. And then I did my master's there. So I loved the program, but I still felt that the gaps that I had, which I had to address, were not done there. But anyway, so I completed my master's, and then I joined industry again. And I continued, mostly I went back to Devdhar Electro Design after a small gap there. But I worked there for about roughly 2.5 to 3 years. And then again, reached a, shall we say, a plateau there. Again, had the same questions that, no, I think I need to really move elsewhere, because at that point in time, I had I would say I had a better idea, in the sense that, no, I think I need to do more into simulations and stuff like that. In fact, that thought crystallized when in September of '93, August to September of '93, I had the opportunity of attending a workshop, power supply workshop held at IIT Bangalore. And that was really a experience of a lifetime. I still remember that, and remember my conversations with Professor Ram Narayan, who also, I would say, that was one conversation I still remember. But that was when I think it sort of gave me a better idea of what I need to do, what are the things I need to learn. So that kind of crystallized during those months. And then, so I think I had a good reason to join both the master's program as well as the PhD program.
Right.
So when I made those decisions. So yes, it was a non-linear path for sure. And I would say there are trade-offs in following this particular approach. Because while on the one hand you are motivated, you know why you want to do a master's or a PhD. And I feel that these decisions should not be taken lightly. You need to give it some thought, because not only are you going to spend a precious amount of your life in time and resources trying to be what you think you want to be, So you need to think about it deeply and then take a conscious decision rather than just flippantly make the assumption, not assumption, but the decision that, yeah, I'll finish my master's and PhD and then I go to work.
Thank you for answering all our questions in such a candid and elaborate manner. Anything that you would like to add to this conversation that we have not covered already?
Well, okay, there's one thing that I would suggest. Learn to say I don't know.
That is a very powerful statement.
That's one thing. It's not very easy to say that, especially for me, because I had to carry the burden of this IIT label thing. But I got over it pretty quickly.
So thank you, Dr. Kamath, for joining us today and taking time out of your busy schedule and supporting us in this podcast and in our project in general. It's been great hearing a lot of different perspectives from you, especially your perspectives from the industry point of view and the multi-domain applications and experiences that you shared with us. Thanks, and we hope to stay in touch, and I hope that this episode would be especially valuable to all our listeners and young engineers in their career trajectory. Thank you, Dr. Kamath.
Thank you, Abhijit, Lalit and Sudarshan, for inviting me to your podcast. I really enjoyed talking to all of you. What I feel is that we should not let this conversation be the end point, but the beginning of another mutually beneficial relationship, and I look forward to that. Thank you all for your time, and I really enjoyed this. Talk to you later. Bye.
Bye.